All right, let's start lecture 21, and this will be the start of chapter 22. And so I think this is some really interesting material and fairly easy to grasp. So I think chapter 22 and chapter 23 will be some good material to learn. We're going to talk about aromatic substitution, and so we've done this in lab earlier in the semester. We did the Friedel-Crafts alkylation, and we did nitration of benzene. And so we will talk about those now in lecture. And so we're going to do what's called electrophilic aromatic substitution. This is abbreviated EAS. And in chapter 22, we're going to talk about on benzene exclusively. And then chapter 23, we'll talk about substituted benzenes and how the different substitutions affect the reaction and the regiochemistry. And so if we look at this, it says electrophilic aromatic substitution. Again, you want to read it backwards to remember what it is. So it's going to be substituting an aromatic ring with an electrophile. And so our benzene ring is going to serve as our nucleophile. Later on, right before the end of chapter 3 material, we'll talk about nucleophilic aromatic substitution, where the aromatic ring is actually an electrophile. And so again, in this case, the aromatic ring will be our nucleophile, and we'll be adding an electrophile. All right, so back in the spring, we talked about using alkenes and treating them with halogens. So we simply took an alkene. It looks something like this, and we throw in Br2, for example. And this would add 2 bromines across our alkene. So we did a bromine on this carbon and a bromine on this carbon. And so we would have a product that looks like this. Now if we take a benzene ring instead, we see that the benzene ring looks like it's made up of 3 pi bonds, but we know that these pi bonds are conjugated, and so benzene is aromatic, and so it does not react like normal alkenes. And so if we take benzene and Br2, we get no reaction. Alright, and that's because benzene is relatively stable, and so if one of these pi bonds attacks bromine, then we lose aromaticity, and so that's not going to happen. Now, if we make our electrophile extremely electrophilic, and so extremely reactive, then our benzene ring will react in that case. And so we take our benzene ring, and we throw in Br2, just like here, it's not going to do anything. And so we need to use a Lewis acid. Lewis acids will make our electrophile extremely electrophilic, which we'll talk about in the mechanism in just a second. And that does allow our reaction to occur. And so we'll use iron tribromide, so FeBr3. This makes our Br2 molecule extremely electrophilic, and so we get our aromatic substitution. And so we've substituted out a hydrogen on our benzene ring for a bromine. And so this is electrophilic aromatic substitution. All right, so let's take a look at the general mechanism for electrophilic aromatic substitution. Then we'll talk about halogenation, Friedel-Crafts alkylation, and other reactions that we can do with benzene. And so we take this, we make our electrophile extremely electrophilic, and so we end up with a electrophile here, and so our pi bond attacks just like we've seen in the spring semester. In this case, remember with alkenes, we could swing out on this carbon or we could swing out on this carbon. In the case of benzene, it doesn't matter, but once we move on to the next chapter, it will matter. So at this point, it doesn't matter. And whatever carbon it swings out on gets the electrophile, and then the other one gets the positive charge. And so we've broken aromaticity in this case, and so then we re-aromatize the system to get back our benzene ring. So there's a hydrogen right here. It's the same hydrogen that it was here. We use some type of base, which I'll just represent with B minus here. That comes and takes this hydrogen and gives us back our pi bond. And so we get back our benzene ring. And now we've done our electrophilic aromatic substitution. All right, the first reaction we'll look at is halogenation, which I just mentioned earlier in the video. And so we're going to take benzene and we're going to put bromines and chlorines on it. And so we can take Cl2, and Br2, and we can put these halogens on the benzene ring. Remember, these electrophiles are not electrophilic enough, so they're not reactive enough for benzene to react with them. We have to throw in a Lewis acid. A lot of times we'll see iron and with the corresponding halide. And so we have iron trichloride if we're doing chlorination, and we have iron tribromide if we do bromination. So FeBr3. And both of these reactions, the one on the top will put the chlorine on our ring, the one on the bottom will put the bromine on our ring. And so we get these two reactions here. In addition to iron, we can also use aluminum. And so we can have aluminum trichloride, which reacts the same way as iron trichloride. Or we can have aluminum tribromide. And so both of these act as a Lewis acid and facilitate this reaction. So let's take a look at the mechanism. Alright, so in our reaction we have benzene, Br2, and iron tribromide. Iron tribromide works as the Lewis acid, and a Lewis acid is an electron pair acceptor. And so we have some lone pairs on our bromine molecule, and those are going to attack the iron. And so the first step in our mechanism is bromine adding to our Lewis acid. In this case, iron was neutral, and we've given more electrons to it, so it gets a negative charge. Bromine was fine here with 1 bond and 3 lone pairs. Now it has 2 bonds and only 2 lone pairs, so it gets a positive charge. And then once that forms, this bromine is extremely unhappy, so it pulls these electrons away from the other bromine. And then we get Br plus by itself. And so we have Br plus, and then we have FeBr4. And so once this happens, now we've gone from a neutral Br2 molecule to a positively charged bromine atom. And so this is extremely electrophilic, and so now our aromatic ring can attack that. So I'm going to draw it again over here. Again, in this case, since it's just benzene, it doesn't matter if it swings out on this carbon or that carbon. I had this carbon attack our bromine, and so our positive charge ends up over here. So now we need to re-aromatize. And it's these electrons that the bromine gave to the iron earlier that come back and pull off this hydrogen. So we make HBr as a side product. And so we have a mechanism like this. So we get HBr, we get FeBr3. So this is a Lewis acid catalyst. And so it goes back up here and repeats the reaction. And then we get out our desired product. And so now we have our substituted bromine. We took a hydrogen off and we put a bromine in its place. So this is electrophilic aromatic substitution. And this is how we put a halogen on a benzene ring. All right, let's take a look at an example. So let's say I want to make the following molecule from benzene. So I need to think backwards till I get all the way to my benzene molecule. And so if I'm looking at this, I know that sulfur acts exactly like oxygen, and so therefore they're almost always nucleophilic. And so if I can make this carbon electrophilic, I can make this sulfur carbon bond. So I'm going to break this bond here. And literally just pull those two pieces apart. Now I need this to be nucleophilic, I need this to be electrophilic. We have a few different ways to make our carbons electrophilic. The easiest way is to put a halogen on there, so let's do that and see if we can work backwards to benzene. So now we have that carbon being electrophilic. It has a good leaving group, and so we could do an SN2 reaction. And our sulfur would need to be nucleophilic. And so we would probably need it to be negatively charged, and so we need some type of counterion, such as sodium, to balance that charge. So we could use this sodium salt here. Now we still haven't got back to benzene, so let's think backwards from here. If we want to get back to benzene, that means we need to somehow make this carbon-carbon bond right here. And so we need this carbon to be electrophilic again. We know that if we put two bromines on there, we're going to get different kind of alkylation products, and so that might not be the best thing to do. We might want to maybe think back to a Grignard reagent possibly. That would make this carbon nucleophilic. And then again, we don't want a halogen on here, so maybe making it electrophilic in some other way, such as a carbonyl possibly. Alright, so if I think backwards to this, I know this is my Grignard reagent, so that would be nucleophilic at this carbon. This would be electrophilic, and so I could make a carbon-carbon bond from here to here. The resulting product of that would be an alcohol, and then I know I can convert alcohols to bromines. And so this would be a plausible way to get to this product. And then we still haven't got back to benzene, so we know we can make Grignards from the corresponding aryl halide. And so we can take this molecule and throw magnesium in to get to here. And then we just learned how to do a bromination of benzene. And so we can think backwards from here. So our benzene ring. And so in the forward sense, we would use Br2 and FeBr3. Then we would use magnesium to get to here. The Grignard reagent could then react with this aldehyde. We need an acid workup step to get the alcohol. FeBr3 would convert it to the bromide, and then the bromide could react with this sodium salt right here to make the sulfur carbon bond and get us back to the final product. Alright, let's move on to talking about the Friedel-Crafts alkylation. And so for those of you in lab, you've already seen this semester, but now we'll cover it in lecture. So again, we take benzene. It's not that reactive, so we have to make our electrophile extremely electrophilic. And so we throw it in with this alkyl halide here. Nothing's going to happen, but we need to use a Lewis acid. That'll make this extremely electrophilic, and then our reaction will proceed. So again, we usually use the corresponding halide. So we have a chlorine here, and so we're going to throw in aluminum trichloride. FeCl3, iron trichloride, would also work in this case. It's going to pull this chlorine off and make this carbon have a carbocation, so it's extremely reactive. And then we make a carbon-carbon bond from our benzene ring to that carbon. And so we have a reaction that goes like this. For the mechanism, what we start with is the alkyl chloride. So this mechanism is going to be exactly like we saw in the halogenation, except instead of having two halogens bound to each other, we have a carbon and a halogen. And so again, the first step is coordination. So our chlorine just adds to the, or attacks the Lewis acid. Since our chlorine now has two bonds, it gets a positive charge. Our aluminum got some extra electrons, so it's a negative charge. And so this just pulls the chlorine off of the carbon atom. So this is a heterolysis step. And so this gives us our carbocation. Carbocations are extremely unstable, and so they're highly reactive. And so once this forms, our benzene ring comes in and attacks it. And so now we've made our new carbon-carbon bond from this carbon to this carbon. We have our positive charge here. And our electrons from our chlorine that are right here are going to come back in and pull off the hydrogen to re-aromatize. And so then we get to our final product. And so in this last step, we make HCl, we remake aluminum trichloride, which can come back up here and do this again. And so this is called a Lewis acid catalyzed process. All right, so let's talk about limitations of the Friedel-Crafts alkylation. If you're in lab again, you've probably seen this before. And so Friedel-Crafts alkylations are susceptible to carbocation rearrangements. Remember, we talked about 1,2 hydride shifts and 1,2 alkyl shifts back in the spring. Remember the numbering, so it's 1,2 hydride shifts and 1,2 alkyl shifts. So we can't move more than from where we generate the carbocation to the spot right next to it. So that's why we call it a 1,2 hydride shift. And so we can't just jump across the molecule. We take a look at this reaction here. We see that we have this alkyl chloride. We throw in aluminum trichloride. And so we may expect that we're going to make a carbon-carbon bond from this carbon to this carbon on our benzene ring. But that is not what actually happens. Instead, we make a carbon-carbon bond to this carbon here. And so you may have noticed this problem in your lab quiz last week. And so we end up with a product that looks like this, where we've added to this central carbon here. And so coming off of that carbon, we have 2 methyl groups and then an ethyl group. And so this would be our major product. And so let's run through the mechanism for this reaction. We take our alkyl chloride and we throw in aluminum trichloride. We have the same coordination step we had earlier. And so we get to something that looks like this. And again, this is going to pull off our chlorine just like we saw before. And so this gives us the corresponding carbocation. We see this carbocation on this carbon has only one other carbon group attached to it, so we call this primary. We know primary carbocations are extremely unstable, and so they're looking to rearrange if possible. This is the 1 spot, this is the 2 spot, and we have a hydrogen on here, so we can have a 1,2 hydride shift. And so now our hydrogen's moved over to this carbon, and our carbocation exists here. So we've gone from a primary one to a tertiary one, and now this serves as our electrophile in our reaction. And so we add our group here to our carbon. This de-aromatizes our system, and so our aluminum species that we generated over here comes back and deprotonates this to make HCl and remake aluminum trichloride since it's a catalyst. And so that gets us to our final product shown here. Now remember, in the spring we said that we never generate primary carbocations because they're extremely unstable. And so this process right here probably happens in the same step. For the purposes of going through a mechanism on an exam, I don't care if you show it as 2 steps or you show it in the same step. But since we never generate these, they probably happen at the same time. And so the actual mechanism would probably not be this and then this. Instead, it would be the hydrogen rearrangement at the same time. And so you would have your hydride rearrange as this chlorine carbon bond is being broken to get you to this tertiary carbocation shown here. And so this would be the mechanism for the Friedel-Crafts alkylation whenever we have rearrangements. And so be on the lookout for this. Alright, so another limitation for Friedel-Crafts alkylations are that we can only use sp3 hybridized carbons to do this type of reaction. And so if we take our benzene ring, we throw in this chlorobenzene, we know that this carbon is sp2 hybridized, and so it cannot participate in a Friedel-Crafts alkylation. Even if we throw in aluminum trichloride, no reaction occurs in this case. Now, if we're thinking about how to make a carbon-carbon bond from our benzene ring to here, we might want to consider a cross-coupling reaction like a Suzuki reaction or a Heck reaction or something like that. And so we would need to put our boronic acid on here, use our chlorobenzene, and then instead of aluminum trichloride, we need some type of palladium catalyst. And so a lot of times you'll see this triphenylphosphine palladium catalyst used. And then again, we would need our boronic acid on here. So our phenylboronic acid. Now we could make a carbon-carbon bond from this carbon to that carbon. And we would have this type of product. And so again, Friedel-Crafts alkylations do not work on sp2 hybridized carbons, only on sp3 hybridized carbons. So that would be the wrong reaction to use in order to make a carbon-carbon bond between two different benzene rings. All right, and the last limitation we'll talk about in the Friedel-Crafts alkylation is that polyalkylated products may occur because after the first alkylation, that resulting product is even more reactive than the benzene ring itself. So we'll talk about this more in chapter 23 because that's when we'll talk about substituted benzene rings and how they react. And so just to show you right now, if we do this type of reaction with benzene, this alkyl chloride, we're going to end up with a variety of different products as you saw in the lab. So you got dibutylated toluenes, you got butylated toluenes, and then some leftover toluene as well. And so our products would be our monoalkylated product, as well as the dialkylated products at both the ortho and para positions. So remember on the benzene ring, if we're talking about a substituent, the two carbons next to it we call ortho. And then the two carbons next to that we call meta. And so I abbreviate those with O and M. And then this bottom carbon that's opposite of whatever substituent we're talking about, we call para. And so we abbreviate those with O, M, and P. And so this type of substitution facilitates ortho and para substitutions. And so we would have a dialkylated product like this, where our two substituents are ortho to each other. And then we would have a product like this, where our two substituents are paired to each other. And so we get polyalkylated products when we do a Friedel-Crafts alkylation.